Today we will see the photoelectric effect and golden rules and the correlation between the photoelectric effect and Fermi golden rule in detail. Earlier, I have used constant perturbation method to prove the uh, Fermi golden rule. Here we are going to use harmonic perturbation because it is more convenient to explain the photoelectric effect as well. Uh, because here we are in photoelectric effect, we will irradiate with the sample with the light of different frequency. So you can understand why we are doing using harmonic perturbation. So harmonic perturbation means the perturbation is sinusoidal one. According to first order time dependent perturbation, the AK of 1, that is uh, coefficient of expansion for first order correction, AK of 1 is equal to 1 over I h cross integral 0 to tau e power I omega km t bra k h prime, which is a function of t, get m tt. So this is the expression we got it for the expansion coefficient for the first order correction. This one represents the first order correction. Now we are going to perturb the perturb the we are adding an additional perturbation which is harmonic one, that is 2 times the sine omega t is we are adding some additional perturbation, and here h prime is function of t, so we are separating the time dependent outside, so this is independent of time. These two I have introduced for mathematical reason. Every time we need not write this bra k h prime km. So as usual, we will write this as h prime sub km. This sine omega t can be written as e power I omega t minus e power minus I omega t divided by 2i. Now you can understand why I introduced these two. Now this 2 can be cancelled, and this I and this I will become I squared. So that is I squared is minus 1. So we can write this as minus 1 over h cross. And as I said, this is time independent, so I am taking out. This integral I am separating into two parts. One is this exponential I omega t, and this. If you multiply both, you will get e power I omega km plus omega tt. This is one integration between the limits 0 to infinite. Another one is this multiplied by this, which is equal to minus e power I omega km minus omega, this omega t tt. So now we will reduce this further. Now we got the expression for expansion coefficient for first order corrections. So this is equal to this one. Now you integrate the first one. So if you integrate this, you will get e power by I omega km uh, plus omega t over omega km plus omega. If you apply the limit tau, this t will become tau. If you apply the limit 0, then minus e power 0 is 1. So e power this is minus 1. Uh, so uh, Here you have one I also. So that I brought outside. Uh, and second term, instead of plus, you will get minus. That's all. K omega sub km minus omega tau divided by minus 1 divided by omega km minus omega. So here, the denominator you can see any one of the term will be dominant. See first, if omega km is approximately equal to omega, sorry, not omega, is minus omega. So minus omega, then the first term will be close to zero. Denominator will be close to zero. This will dominant. And if it is other way around, that is omega km is equal to omega, approximately equal to omega, then the second one will dominate. We will take the first case because there is a meaning. I will explain why we are taking first one. We take this condition omega km is approximately equal to minus omega. What is omega km? Omega km is 4 angular frequency, which is by definition initial energy ek minus final energy ek minus initial energy em over h cross and plus omega, which is approximately equal to or close to zero. So this will become, this term will get dominated. First term will get dominated. Then we can ignore the second term. First term will get dominated. Then you can ignore the second one. So now, if you multiply this by H cross, then you will get Ek minus Em plus H cross omega equal to 0. So, which indicate if you bring to second and third term to the right hand side, these two, to the right hand side, you will get Ek is equal to Em minus this plus will become minus H cross omega. So this means final energy is less than initial energy. That means it is a stimulated emission process. So you take only the first term. We are interested only in emission process because it's a photoelectric effect. When you shine the light, it will emit the electron. Electron will go to higher energy state. So take the first term alone and ignore the second term. Now we have taken the first term alone. Uh, we have ignored the second one because we are dealing with stimulated emission, which is very essential for photoelectric effect. So we have taken only the emission term and we ignored the absorption term. For further detail, you can refer my earlier lecture on harmonic perturbation. Now, the probability of finding the particle from mth state to kth state, initial to final, that transition probability is equal to modulus AK, AK1 square. So if you square it, 1 over IH cross square will become just 1 over H cross square. And this is modulus H prime Km whole square, and this if you square it you will get this exponential term minus 1 squared divided by omega km omega whole thing squared. So using the fact that we know very well that e power I theta minus 1 whole square is equal to 4 sine squared theta pi 2. So we are using this relation here. So here 4 sine squared, here theta is theta is km plus omega tau actually. Km plus omega tau, this is theta. This we are taking as theta, except this I. So theta by 2, you remember there is 2. So 1 over 2 we are taking and 4 we are taking. 4 sine square theta, sine square 1 over 2 omega km divided by, omega km plus omega into tau. This above equation, if you replace this in the numerator, you are replacing by 4 sine squared this term omega km plus omega tau divided by 2, and the denominator you are squaring it omega km plus omega whole square, and you are taking h prime h prime km modulo square divided by h cross square. Of course already you have taken this 4 here. So this is the uh, transition probability from moving the initial position to final position. Now we will reduce it further. We have seen that transition probability from m to k, which is a function of tau, is equal to 4 times h cross sub km whole modulo squared sine squared omega km plus omega tau over 2 divided by omega km plus omega whole square. This is for the transition between two discrete states. So now in photoelectric effect, we are going to see the transition between a discrete state, that is here discrete state to continuum state. So previous case in harmonic perturbation, uh, we have taken the issue that transition from one found state to another found state, that is initial found state to final found state, that is discrete state. Now the case is slightly different. And as I said, why we have taken the harmonic perturbation is we are going to shine the light which has some frequency. So we have taken the harmonic oscillation. Uh, the total transition rate associated with the transition from a initial state UM into a continuum final state UK. We are going to see this, and where the here the rho which is a function of ek, that is final energy, is density of final state, that is number of states per unit energy interval, that is number of final state within the energy interval ek minus tek and ek plus tek between these two level. Then the total transition rate gamma m to k is we have to find. First discrete case, if you shine the light, say for example you are taking the semiconductor, you are shining the light on the valence band. So this one electron will go to the conduction band. So it's a emission process. So we have taken, if you remember that we have taken only the first term, we ignored the second term, which is absorption. Here electron is emitted from here to here. It is for discrete level. Now, what will happen to the continuous level? That is, final state is continuous. We can take initial state also, because valence band is contains so many state. Uh, you can take the initial state also continuum, but that problem will be little bit complicated, and it will not affect your result also. See, you are not at all worried about the initial state. Uh, Whatever the number of electron here, it can reach here only if that particular state is empty state. Otherwise, you cannot accommodate. So here you have density of state. If you have more density of state, you can accommodate more number of electrons. So it is naturally it depends on number of state available here. Say for example, in the case of intrinsic semiconductor, conductance band is completely filled and valence band is completely empty. In the case of n-type semiconductor, you have already a few electrons in the conduction band, so you can transmit only few electron to that energy level. Now we will come to our problem. Say, let us say you have the energy state Ek here at the center, and continuous state is between this. Let us say this is minus Tek. That is energy difference between this and this is equal to more precisely we can write this is ek minus etk. Then I will use different color, so that is here it is 1 minute, sorry, here it is tek only, but ek plus tek. So now the transition rate is, by definition, transition rate is this probability, transition probability per unit time. So probability, this yellow shaded parameter, that is transition probability per unit time. That is the rate of transition. But however, here in this case, rate of transition also depends on the density of final state. So if there is a available state, then only you can have a transition from here to here. Otherwise, you cannot. If it is completely built, there will may not be any transition. So transition is proportional to naturally the density of final state. So we have taken a small energy interval. So we are going to integrate it between the limit ek minus tek and ek plus tek. So we are integrating over tek. Now you take 1 over tau outside because it's a constant, and you substitute this pm to k. Pm to k is this one. For h prime sub km modulus squared sine squared uh, omega km plus omega tau over 2 divided by omega km plus omega k squared rho e of k tk. And now we will try to reduce this further. Now, uh, now we got this expression uh, that is a gamma mk, rate of transition from m to k states is 1 over tau. Time being you ignore the red color bond term. So integral between ek minus tek to ek plus tek, 4 times h prime km km modulus squared over h cross squared sine squared omega km plus omega tau over 2 divided by omega km plus omega squared rho rho of e k t k. Now I am going to multiply and divide by tau squared by 4. So tau squared by 4 I am dividing and multiplying. You can understand reason for it. See, I want to keep this as x. Augment of this sine theta is x. This term is x. then naturally the denominator, this one, will become x squared. That is square of the argument of this sine squared theta, sine squared. Then another substitution I am going to make is this TEK. TEK is very small, so I can take this as H cross omega, that is T omega. I have not used T omega k because TEK is very small. I can approximate this as H cross T omega. Now we have taken this as x. That is x is equal to omega km plus omega tau divided by 2. If you differentiate this with respect to T omega, then Tx is equal to tau over 2, because first term is not depends on omega, so this will be 0. The next term will become t omega, of course with constant tau by 2. So then t omega is equal to uh, 2 over tau. If you bring this to the other side, you will get 2 over tau tx. So what I am going to do is I am going to replace d omega as c. This d omega I am going to change to 2 tau pi x. That is, this I am going to replace pi 2 over tau 2 over tau dx. So now after substitution, you can find here that is this will become sine squared x, because argument we have taken as x, and this is naturally x squared. So this will be x squared, and rho e of k here we have seen that this is h cross 2 over tau dx. Now we can cancel some of the constant, that is uh, here you can see tau, and here we have one tau will become tau square, which will cancel with this tau square, and here you have 4 and here you have 4 will get cancelled. Then here you have one h cross, which will cancel with this h cross square. Now, since x is very small, you can change the limit from minus infinite to plus infinite and bring all the constant outside the integral. What are the constant here? You have 2 here in the numerator, 2 multiplied by this h prime sub km modulus squared, because it does not depends on x. So, and this h cross. So, this 2 and this h prime km modulus squared over h cross, this h cross, and rho e of k. This also does not depends on x. So, we are taking out, and since x is small, we are taking the limit from minus infinite to plus infinite. So this is the standard integral. This integral value, you know very well, it is pi. So now I am replacing this integral pi. So then this will become 2 pi over h cross, the h cross km modulo squared rho e of k. So this is exactly what we got using the constant perturbation method. Here we obtained the same thing using harmonic perturbation also. So you know very well that physics does not change whether you are using some method X or Y. Whatever may be the method, you will get same result. You got exactly same result. What you got for constant perturbation. Here we have used harmonic perturbation. Reason I have already explained, because we are signing the light of different frequencies. So I have taken the sine omega t as additional perturbation. We are signing the light. So we can take cosine also, not necessarily sine, cosine. Cos omega t. If you take perturbation as cos omega t, also you will get same result. Thank you very much for watching my video and supporting me continuously. Thank you very much.